Okay, so so the last lecture we were talking about mainly how quantum unitary operations work, and we made a small start on this set, which is finally talking about quantum gates. So let me just recap a little bit about how quantum gates work. So what I was saying in the last few minutes of last lecture was that generally, the law of nature is, in terms of quantum mechanics, is Schrodinger's equation. But previously, until fairly recently, this was considered not really sort of a controllable thing. It's sort of something that's sort of given to you by nature. But more recently, people have been able to people have been able to control like the Hamiltonian, and so people have been able to sort of design this Hamiltonian and hence the type of evolution that a quantum system can be put into. So essentially, this is what a quantum computer is. It's kind of the ultimate controllable quantum system. So we have a bunch of qubits, and if we are able to control those qubits in basically any way that we want as desired, then we've basically achieved our task of making a quantum computer. So basically what I'll be talking about in this lecture is how do we control a quantum computer in general. So so before we talk about quantum gates and things like that, I just want to give you a little bit more of a physical picture of what types of things we might be controlling. So what is the physical system that we're talking about? So this can be still really many things. So quantum computers are not developed actually to the stage that we're even quite sure how to make a quantum computer. There are some sort of leading candidates, but still people are trying all different types of technologies, and who knows which will be the eventual winner. I think I probably told you about the same thing was true for classical computers. People thought of making classical computers out of all kinds of things, gears and mechanical systems to more electromechanical systems like relays, and then finally, of course, now we have probably hit upon the best possible technology, which is essentially integrated chips and transistors, the modern day kind of computer technology. So quantum computers are still not at that stage. So these are just possible systems that could be used to make a quantum computer. So first kind of system that you might think of is to use atoms. So using the energy levels of an atom, or it could be some people try to make quantum computers out of light. So light is also ultimately a quantum object. So photons, which are like the particles of light, people are able to now actually create sort of single photons quite effectively. So there are such things as single photon emitters, and then even then it's you can still encode the information in many different ways. So you could encode the information in the polarization of the photon, or it could be even like which path it goes down. So you've got this beam, these are beam splitters. If it goes down this path, it's logical 0, and if it goes down this way, it could be logical 1. So that's another approach. And so there's many different even approaches within photons. Solid materials, people consider this for sort of qubit technology. technologies, and the main one I'm thinking of are things like quantum dots. So this is within semiconductor systems, you create sort of certain, say, impurities, and then the impurities act like qubits. And so you can engineer these types of semiconductor systems to create qubits. And people that do this, usually the way they kind of, one of their selling points is that, we've made regular computers with silicon, so making quantum computers with silicon, we can transfer all that technology, and so that's why it's a good thing. Not everybody agrees with that, but everybody puts up their best argument for why their system is the best. Another one, maybe this is not so much quantum computers, but still sort of related kind of devices for quantum computers. You can make these sort of tiny kind of structures. So these are like some kind of floating sort of bridges, right? So this is kind of floating, as you can sort of see, and these little kind of pieces of tiny sort of string almost vibrate in certain ways, and then you use the vibrational modes of those things to encode information. People do that kind of thing. Diamonds is also another very well-known system. So it's not actually the diamond, it's actually the defect in diamond. So when you have a piece of diamond, originally the natural pieces of diamond that you find in the earth, they're formed by taking carbon and exerting a huge amount of pressure on them, right? And then somehow this structure forms. But of course, our atmosphere is full of nitrogen, and nitrogen is can sometimes sort of accidentally get in the mix here. And nitrogen has like 3 bonds, but carbon has 4. So there's a sort of missing bond here, right? So that missing bond is that's next to the nitrogen atom. So these are called NV centers. It stands for nitrogen vacancy centers. It's a vacancy because there's a vacant sort of site here because of the nitrogen with only 3 bonds. So that can act as a qubit because there's a sort of an unpaired electron there. And this actually has quite good properties, and I'm not sure if it's really great for making a quantum computer, but it's really great for doing things like you put little bits of diamond inside like biological systems, right? So because diamond is quite inert, it's not poisonous or anything. You can put it inside some small animal, maybe even yourself, and then you can actually measure things around it because you've got this kind of qubit inside the diamond, and that can be used for measurements. So actually quite a nice technology. Superconductors, and maybe this is the leading candidate. So for those of you doing the IBM Q, this is actually what the physical system is based on. I'm not really going to explain how it really works, but basically you have like a superconductor, and then if you make circuits out of the superconductor, the circuits actually become kind of quantum systems, and because the circuits themselves are quantum, you have sort of energy levels again, the discrete energy levels, a bit like the atom, and then so you use those as the qubits. It turns out somehow that this one is the leading one today, and Google, IBM have taken up this particular technology. But who knows what will be the technology? My bet is on atoms still, so that's the system we're working on. But nobody really knows. Okay. This is sort of more or less my one. So if you cool down atoms to very low temperatures, they have high coherence. So there's this special state called Bose-Einstein condensate. I won't go into so much, but it's sort of like it's sort of as if you are making a laser out of atoms. So a laser is something where light is becomes a very coherent kind of system, right? Because the laser, basically the waves of all the photons kind of go spontaneously in phase, right? And basically this is sort of like the atom version of that. So we know that atoms are very useful for, we know that lasers are very useful for various technologies, so it's kind of reasonable to expect that maybe the atomic version will also be quite useful. Okay, but let's, all right, so that's just to give you a bit of a flavor. I mean, nothing really, no equations or anything, of you know, what we might be talking about in terms of building a quantum computer. So now let's get on to a little bit more of the actual nitty-gritty. So a quantum computer is, as I said, it's sort of the ultimate in controllable quantum system. And just like we learned before with like the composite systems, so if you bring together a bunch of qubits, then the system can all form like one quantum system, right? And say we brought together 8 qubits like this, then there are a total of 2 to the power of n different states, and it's easy to see anything from all of them being 0 to all of them being 1. Right? So we can write this sort of as a binary number, if you like. Yeah. And it goes from, or if we convert that to a decimal number, for 8 qubits, it would be 256 states, right? Starting from 0. So the general quantum state of such a quantum computer would be basically some wave function with 2 to the n of these components, right? So these A with the subscripts, these are all the different coefficients of the states. Each of those can be some complex number, as we're all familiar with now. And so I could write it sort of like this, where this n is just like 0 or 1, so these are all different combinations. Or I could just label this whole state as just that decimal number from 0 to 255 in the case of 8 qubits. So we can think of our quantum computer at any given point in time to have this state there stored in the quantum computer. And basically what a quantum computer does is basically execute this sequence at the bottom. So we start with some input state, and there's some kind of quantum algorithm that we perform. And so, as we've learnt sort of in the last set of lectures, basically an algorithm is just some kind of unitary operation. And it needs to be unitary because ultimately, Schrodinger's equation is the kind of the underlying physical sort of underlying law, right? So, whatever we're doing here, of course, still has to follow Schrodinger's equation, and then Schrodinger's equation is always some kind of unitary sort of matrix. So basically what algorithm we're actually doing just corresponds to some kind of unitary matrix. And that is going to be applied on this input. And then we get some kind of output state, so it's our final state. And of course, you need to actually measure something there, right? So ultimately, so that we can understand what has just happened, we need to do a measurement. And so in general, we do the measurement, and then there'll be all these different outcomes with probabilities according to whatever that wave function is, with the usual law of the modulus squared of the coefficient. So any quantum algorithm is more or less that. course, it's all about the algorithm. I mean, in fact, any classical algorithm is also something like this too. You've got your input data, computer does some number crunching, or some algorithm, you've got some final output, and that's the thing that you wanted. Normally we don't think about measurement so much because we take it for granted that we do the measurement, but quantumly we need to think a little bit more about the measurement. Okay, so what is this U algorithm that I just said? So it's unitary matrix. In general, this matrix could be all kinds of different matrices, because all I've said is that it needs to be unitary, and that's because it needs to follow Schrodinger's equation. But there's so many different possible U's. How in the world are we going to prepare all these different U's, the unitary matrices? And basically the strategy that we follow is in the same way as we do classically. So classically, also, we could have, obviously, there's a lot of different algorithms out there, so it's sort of an infinity of different algorithms. So how do we build algorithms? Well, we build them out of simpler gates, right? So we have some simpler set of gates like AND, OR, NOT, and so forth. And we combine all those gates, and by combining the gates, firstly, that's kind of an intuitive thing for us humans to do, rather than, say, okay, I want an algorithm that does this. Okay, here's my matrix. Boom. Like that's a little bit, it's not really humans are not really able to deal with work like that, right? So humans like to break things down into smaller and smaller problems and say, okay, I know how to do this. So we combine that box with this box, and then I know how to do that, so I combine those two boxes, and then, so you build more and more complicated things by sort of combining boxes that do simpler tasks together, right? This is how we do anything complicated. So, so classically, that's what we do. So also, quantum mechanically, that's also what we're going to do. So we're going to make quantum gates that do sort of these elementary steps, and then we combine things up to make something more complicated. So, what I'm going to do is kind of contrast this sort of classical gates with the quantum gates, and I think that's maybe the easiest way to sort of understand why we deal with the kind of quantum gates that are commonly dealt with. So, so are you guys, familiar with sort of this kind of gate logic stuff in general? Seen it before?
Yes, in computer science.
Right. Okay. Yep. So okay. So for those of you not familiar with it, it's it's not. When I first did it, I thought, okay, this is kind of nice and kind of easy stuff. I thought, in a way, I thought it was quite intuitive. But basically, you would have heard about things like AND and OR gates, right? Yeah. So AND and OR gates are sort of two fundamental types of digital gates. And there's a famous result that says that actually you can actually make any algorithm ultimately out of actually only one gate. So there's the NAND gate, which is defined as the opposite of the AND gate, right? So if you've got 0, 0, then the output is, for an AND gate, these three would be 0 and this would be 1, right? Because for AND you need both the inputs to be true for the output to be true, right? So for the AND gate it will be 0, 0, 0, 1. The NAND gate, which is just the opposite of the AND gate. So you just flip it. So it's 1, 1, 1, 0. So if we have that one gate, we can actually make any gate, any other gate, and furthermore then, if we've got all the different 2-bit gates, then actually we can make any circuit even, right? So it's in principle possible to build any algorithm actually just from NAND gate. So it's kind of an interesting result that you only need one type of gate to build any algorithm, right? So for example, you don't have to worry about the, why it's like this, but you can just believe me that, for example, the OR gate, we can combine 3 NAND gates and then make a gate like that, or a NOT gate, for example, combine the inputs, then it's also it becomes a NOT gate. So so what is the analogous result for quantum computers? So it turns out actually you need 2 gates for quantum computers because the rules are a little bit different. So it turns out that actually, and I won't really go into why, but or prove it, but you can make any algorithm, algorithm, by combining 1 and 2 qubit gates. So long that you have a 2 qubit gate, and this is supposed to be some 2 qubit gate here, and you combine that with 1 qubit gate. This combination of having 2 qubits and 1 qubit control, you can actually make any algorithm, as in you can make any unitary matrix that you like just by combining those 2. So it's kind of a famous result of quantum computing. So that's why we're going to only really talk about 1 and 2 qubit gates. So because basically we're relying on the result that we can combine those and make anything more complicated. Okay, so let's start with 1-bit gates. Eventually 1 qubit gates. So this is, I'm just doing classical gates at the moment, okay? So for 1-bit gates, actually you can write down all the possible gates just in one page because a 1-bit gate has 2 possible inputs and 2 possible outputs, right? So that's all that there could actually be. There are no more 1-bit gates. So either the gate does nothing, okay, so 0 becomes 0, 1 becomes 1. Or you flip the input, so 0 becomes 1, 1 becomes 0. Or it gets reset to 0, so no matter what the input is, the output is 0. Or you reset to 1, so no matter what the input, you output 1. And in fact, that's all that there can possibly be. And so, suppose we were trying to invent quantum computers for the first time. This might be the thought process that you go through. So you go, okay, fine. That's all the classical 1-bit gates that can possibly be. So let's make the quantum versions. Okay, so let's start from those 4 and see if we can make the quantum versions. So quantum versions, we're going to have like some arbitrary input qubit, alpha and beta, and we can certainly make the quantum version of the do nothing. So that's just the identity matrix. So alpha beta becomes alpha beta. Okay, certainly do that. We can also certainly do this one, the thing that flips the bit. So we've encountered this X gate a few times. So the X gate is actually exactly sort of something like this NOT. So if we had alpha beta, then the output is like beta alpha. So it inverts the coefficients. We could also write down this reset to 0, and in terms of a matrix, it would look like this. So basically, no matter what the input is, the output is going reset to 1, 1 is also something like this, where the matrix looks like this, and the output is always like this. Now, do you notice something a little bit weird about the bottom two?
Yes, because the zeros they should have like a length of 1, but alpha plus beta it has the length of alpha plus beta.
Yeah. Exactly, yes. So the output state, if we use this matrix, it's not normalized, right? And you can probably kind of see that, okay, is it because I chose 1, 1? What if I chose some other number? Basically, not really. There's basically no way to choose that matrix such that it's going to be, a normalized state. And so that's sort of, you sort of write that and you go, that already looks weird, sort of warning signs, alarm bells. And indeed, if you think about it a bit more carefully, then you can see that actually this is not a reversible operation, right? So, and you can see that it's not reversible because say you were here, you put in some state, and then the output is always 1, right? And then if the output is always 1, how can you possibly know what it was at the beginning, right? It might have been 0, might have been 1, might have been the superposition with alpha beta, but you're always just getting 1, right? So it's clearly not reversible. And if it's not reversible, it's not unitary, because we know that one of the properties of a unitary is that the inverse of the unitary is the Hermitian conjugate, and that's also another unitary gate. So it's not a reversible kind of process, and if it's not unitary, then it doesn't follow Schrodinger's equation. So basically, these processes actually are just not quantum processes, or at least they do not follow the Schrodinger equation. There's no Schrodinger equation that you could write such that you make it do this.
So,
Yeah.
So does this mean that a quantum computer cannot, like it could reverse, but like a classical computer, sometimes the circuit cannot be reversed?
Yes, yeah, exactly, yes. So a quantum circuit, generally, you do need to write it so that it's actually reversible. There are kind of ways of actually doing this to make things reversible, even if.
So you can never delete anything cleanly in a quantum computer.
In a way, yes. In a way, yes. Yeah, in a way. But actually, there are actually ways of doing something like this. Basically, the trick is that you need to add some more qubits into the system. Okay, so the kind of thing that you can do if you really did want to reset to 0 or 1, and actually this is a kind of important process because, as we'll see, generally a quantum algorithm always starts with 0. And so how do you prepare that, right? So, there are ways actually of doing this. What I'm basically saying here is that if the 1 qubit was all you had, this would kind of violate the laws of kind of quantum physics. So, but with more qubits, then actually you can do this because basically the kind of thing that you do is you kind of push the 1 away elsewhere, right, into some other qubits where you don't really care. But anyway, as far as sort of gates, essentially these two bottom gates are kind of not allowed. Like you cannot have gates that do this. Yeah. Okay, so but the top two are fine. So we certainly can have the gate, not much of a gate, doesn't do anything. That just does nothing. So that's the identity operation. And we're going to start introducing this quantum circuit notation. So basically, if you see like a horizontal line like this in a quantum circuit, then that basically means all that stuff is just identity operations. So nothing is happening to the qubit. We can also have a NOT, so the symbol for that is just an X. But there are a few more types of gates, and we encountered X already, and then also Y and Z. So Z is actually also another gate, so is Y actually. And this is kind of a very much a quantum type of gate, as you can see, because what's happening is that it starts from alpha beta, and then a minus sign is added on the beta, right? So, of course, classically, that's there's no such thing as adding a minus sign to the state. So this is really a purely quantum kind of gate. Another one, which is very commonly used, is this so-called Hadamard gate. And this is a type of gate that it's very often used because what it does is, say you start with state 0 and then you apply this Hadamard gate, then what it does is it produces this like even superposition. So if you multiply this state by this matrix, then you get an even superposition of 0 and 1. If you start with the other state, then you get the state but with a minus sign. And it needs to be these two states, well, or rather, you need this minus sign because otherwise these states would not be orthogonal. And for any unitary, or any of these gates, which are unitary operations, basically if you start with orthogonal states like 1, 0, 0, 1, then you always end up with also orthogonal states. So everything is always orthogonal because basically all these gates in some kind of high dimensional space are all some kind of basis rotations actually. So it starts with coordinate systems with orthogonal, the gate acts, and then now it's like in this case it's sort of like 45 degrees, 135, it's still orthogonal. And you can see that these are reversible because actually if you just apply the same gate twice, then you end up with the identity. That's also true of this Hadamard gate. Actually, there's even more one-qubit gates. So those are just simply the common gates. And in fact, we can write down actually all the one-qubit gates in this way. So we won't really go into the details so much, but just so that you know that such an expression exists. So if you have this particular operation, which you can see is just a particular example of Schrodinger's equation. It's e to the minus, okay, it's plus here, but either the I ht, so the Hamiltonian is just all that stuff there. And what basically this does, and it's nice to visualize this on the block sphere, essentially what this is what this achieves is some kind of rotation of the state around some axis. So you have some state somewhere initially, and then this n parameters, that's some kind of unit vector, and that just specifies what the axis here is. So this would be some funny axis, maybe involving Z and Y or something. And what that would do is that it would take this state and then rotate it around that axis. So this would actually be the most general single qubit, one qubit gate. And the angle that it rotates this around is just whatever that coefficient there is. Okay, but often, we don't really use this most general one qubit gate. Often these are quite common kind of gates that you might see in a quantum circuit. Okay, so that's pretty much the end of the story for one qubit gates. What about two qubit gates? So let's kind of do the same thing. Let's start with the classical 2-qubit gates. And let's look at just some common 2-qubit gates like AND, OR, NAND, and XOR. So AND is, as we said, the output is, all zeros, except when both are 1. OR is sort of the other way around, where it's only 0 here. NAND is the opposite of this one. And XOR is like OR, except that if they're both true, then it becomes false. Okay, so these are, none of these are reversible, right? And the reason why is because, well, you've only got one output, right? So reversible means, okay, if I didn't know what was coming in here, could I work out what it was, right? Okay, definitely, it's kind of impossible, right? Like if you could only see the orange, there's no way of working out what the input was, because well, there's 4 outcomes, but there's only kind of two, like one variable, right? Binary variable. So if it's 1, and I didn't know which one, then I had no idea which one of these 3 cases would be. Even for this one, if it was 1 for the XOR, I couldn't work out which one of the inputs it was, because there's two cases with 1, 2 cases with 0, right? So it's kind of like too many degrees of freedom and not enough information. So so we need to kind of fix this up, because clearly we're not going to get anywhere in this case, right? We're not going to be able to make any 2-qubit gates. So let's do this trick, okay? So how about, okay, at least to give ourselves a chance that it's reversible, how about we just like copy through this first one, but at least we've got like 2 variables to deal with, because this situation was hopeless. Clearly with only one binary output, we're never going to be able to work out what 4 possibilities are. So this at least gives us the 4 possibilities. Okay, so now let's see if any of these are reversible. So let's look at AND. Okay, so is this one reversible?
Maybe not.
That's correct. So why is it not reversible?
I think if there is 2 cases where the output are exactly the same, then it will be possible.
Yep, exactly right. Yeah. So here we've got 0, 0. So it's like we don't know what's happened. We just got the 0, 0. Can we work out what it was before? Well, there's 2 cases, so it's ambiguous, right? So we can't work out if it was that one or that one. Okay, so AND is out. What about this one? Is this one reversible? No. Because
the 2 outcomes are the same.
which ones?
One.
Ones, yeah. These ones, there's a duplicate entry there, so that's not reversible. And this one?
Yeah.
No, okay. 0, 1, 0, 1, yep. And this one?
This one seems reversible.
Yeah, this one actually is reversible, because we've got 4 distinct outcomes, right? 0, 0, 0, 1, 1, 0, 1, 1. So those 3 are gone, but the XOR has a chance, right? So the XOR indeed is one that you can actually make with that's consistent with Schrodinger's equation, and in the context of quantum computing, this one is called not XOR, but it's actually controlled NOT. Okay. It's actually the same logical kind of structure, but it's called controlled NOT. And the reason why it's called controlled NOT is the way that you can think of this is that let's say that the first qubit is the kind of the control, okay? And the second one is the one that we're going to either apply a NOT operation on it, so NOT means we flip the spins, or we don't. And so basically it's like, so let's have a look at this. So this first one is it just sort of goes through and nothing happens to it. Second one, you flip it if the first one is 1. So let's look at the first 2 columns of this table here. So we can see that so firstly in 1 and in 1 copy, which is the output over here. So these are exactly the same, as you can see, right? 0, 0, 1, both of them. This in 2, which is the bottom leg here, it's the same if the first one is 0, or it's flipped if the first qubit is 1. So basically, it's the controlled NOT. It's basically like a NOT on the second qubit, except that it only happens if the first qubit is 1. So we can write that as a matrix. So it just looks like this. So you can see over here in this first top 2 by 2, it's just like identity, and the bottom 2 by 2 here, it's like a NOT or X. And so that's just basically what it does on the 4 logical states. Of course, in general, what this thing does is it takes an arbitrary quantum state with coefficients A, B, C, D, and then produces a new quantum state of A, B, D, C. So it kind of flips these bottom 2. Okay, so this is basically, one of the most important kind of 2-qubit gates for quantum computing. So definitely worth knowing. So let's just quickly work out what this does, just a little bit of practice. So let's say we start in this state plus, which is the superposition of 0 and 1, and then we apply CNOT. What is the output state?
Plus 1.
Well, okay, it's a 2-qubit state, right? So
I see.
what is the 2-qubit output state?
I mean, it's a 4 by 4 matrix, and the upper one is like the plus.
Okay, how about you just tell me what the state is?
How do you describe a 2-qubit state?
Well, a general 2-qubit state is like I sort of wrote down over here, right? So if it's A, B, C, D, so that's the most general 2-qubit state I can write down.
the notation of the quantum computer and the circuits is like the second like the for if we have two qubits, for the first qubit it starts with 0 and there is like 0 and 1 two situation, and for the second it starts with 1, like, and for the third it's like maybe if there's third qubit there's like 1 1 1 or so.
Yeah. So over here, basically, like if I were to write a quantum circuit like this, right, and a question is like
So
this,
the,
right?
yeah, so the 0 for the second state is like the 1 0 case.
1 0. So this. So yeah, in the quantum circuit, when I write it like this, we have to establish some kind of regular convention. But if I call this one 1 and 2 from top to bottom, right? Then this one is talking about always this first variable. And remember, when I write 1 1, what I actually mean by that is like 1 where this is the first qubit, this is the second qubit. So this state would correspond to the first qubit being 0, second one being also 0. This one corresponds to the first one being 0, this one being 1.
So that means we have to rewrite the 0, 1 composite state into like 0, 0 composite state.
0, 1 composite state.
Is it like junior basis?
Um,
Like this one.
Yeah, so that's correct. That's correct. But maybe that's not because this, yeah. So this state in vector notation is simply this, right? A, B, C, D. Right. So if there's a superposition of say two terms here, right? So let's say this one and this one. Then there would be two elements that are non-zero in this vector.
Final answer.
Right. Yep. So how did you get the final answer? Did you do it by matrix multiplication or?
No, just interchange the two.
Right. Yep. Yep. Okay. Yep. Yeah. So so that's correct. So firstly, this initial state is 0 plus 1. Okay. So square root of 2. So that's our initial state. Or in this notation, where I just don't worry about writing the tensor product, I can write this also as 0, 0, just basically keeping the order of these consistent, right? 1, 0. Right. And then if I wanted to write it in this matrix notation, then basically this is a vector with the elements of 0, 0 and 1, 0, and everything else is 0 actually, right? So this first one is 0, 0, third one is 1, 0. So in other words, the vector is like that. I'm just doing it all possible ways of writing it, just so that it gives you the idea, right? Okay, and then now we're going to apply the CNOT operation. So, okay, so if I were to write it like this, then if I did it the matrix method, well, if I knew what the matrix was, right, then I'd just multiply this thing by that CNOT matrix, and I guess I've already done the calculation there. What this does is to invert these last two elements. So in that case, the output is that. But actually, that's probably not really the way that I would do it, because, you know, I don't really always remember what this matrix is, and there's a sort of a simpler way to do it. And the simpler way to do it is just to kind of remember this rule of the CNOT, that if the first qubit is 0, then do nothing, right? If the first qubit is 1, then flip the second qubit, right? So basically, all I have to do to know what the operation of the CNOT is just look term by term and say, okay, you know, is that 0 or 1? If it's 0, then don't do anything. If that's 1 though, then flip this one. So then it's simple enough to write down the output state, and of course these are the same, because 1, 1 is the last element according to this convention here. Okay, makes sense? Yep. Okay, so I think that's just what I said. Yeah, so for me, yeah, this bracket method is sort of the more preferred method, because I find it simple. Oh, is that it? No, that was it. Okay. Just check that was the last slide. Yep. Okay, well, we've got still 20 minutes, so we can just get started on the next one. Okay, so those were the kind of gates that we're mainly going to be using to build up all kinds of different quantum circuits. So the kind of the key result here was that by combining these two types of gates, 1 and 2 qubit gates, we can actually make any arbitrary quantum circuit. Actually, what you need is you need any 2 qubit gate. So usually, what people do is just use this CNOT gate. Right? And actually, for the 1 qubit gates, you actually need a couple more gates like this. Those are just 3 examples. And so if you have like completely arbitrary rotations for 1 qubit and the CNOT, then you can build any quantum algorithm. So actually, those 3 are not quite enough. So sorry, maybe this slide is a little bit misleading. But the statement that if you have a 2 qubit gate and any in a sort of an arbitrary rotation, then yes, you can. So as I said, the general kind of structure of a quantum algorithm sort of more or less looks like this. And let's be a little bit more specific about the types of quantum gates. Hold on, just, yeah, okay. So I'm going to be a little bit more specific about the input state. So even though I said something a bit similar to this before, so I'm going to further say that in fact all the initial states we can initialize to state 0. And I'm also going to make a little bit more of a what appears to be an assumption that the output measurements are all done in the 0, 1 basis. Okay. So these look like some kind of assumptions I'm making, and what I'll show you is that in fact it's not really an assumption. This is still perfectly general. And I'm going to slightly simplify my measurement device notation from this box to just the meter. This is a little bit more conventional when you are dealing with quantum circuits. Okay, so this is sort of what I might call standard form of a quantum circuit. So you have basically initial states which are all 0, and then measurements are always in the 0, 1 basis, and then some algorithm in the middle. So what do I mean by the algorithm? So typical algorithm will look something like this. So some combination of all these gates which we just talked about. Z, X, H. This is just some random algorithm that I made up. So I don't really even know what it does. Probably nothing very useful. But typically, it might look something like this. Just some combination of all these different gates. And yeah. And when we write a quantum circuit, then there are some sort of conventions and sort of assumptions that are kind of employed, and so let's just go through those. So firstly, whenever we write a quantum circuit like this, we are kind of implicitly sort of thinking of sort of time going from sort of left to right. Okay? So you start always with the left side being your initial states, and then you sequentially, you apply these different gates in the sequence as specified by the circuit. And so generally it doesn't matter. So like the length of these lines don't particularly matter, because remember actually these lines are like unitary gates. It's basically like sort of do nothing. But of course the order of actually doing these gates does matter. So you should get the order of applying these gates right. And sometimes it doesn't really matter, for example, that you say you did this H and then the CNOT, right? Or the CNOT before the H, sort of a bit ambiguous how I write it. Actually, in this case, it doesn't really matter because they're on totally different qubits. So in this case, it doesn't particularly matter if you like move these gates like before or after, so long that it doesn't hit any other gate. So you can think of all these gates as being somewhat movable, at least in the sequence. But of course, this X here, you can't push that forward. Okay. So generally, we're executing gates starting left to right. Then finally, at the end, we're doing some measurement. As I said, these horizontal lines just sort of just do nothing, because this actually means identity matrix. And unlike sort of classical circuits, where you might see things like, well, you definitely see things like this. I'm not sure if you see things like this, but there are definitely no loops like this, because as I said, everything is sort of going forward, left to right, and if you got these loops, then this implies something is going backwards in time, so that makes no sense. So in that sense, you can't have anything like this. You also can't have anything like things sort of branching out, because after all, each of these ones represents a single qubit, right? And if this one splits into two, this would sort of mean that the qubit is sort of splitting into two, and I don't really understand what that would mean. Nor this one doesn't really make sense either, because you can't have two qubits turning into one qubit. Okay, so let's talk a little bit about this initialization of the state. So I said that the initial state is always in the zero state. So why couldn't we have a more general state like this? Why couldn't we, surely we could just start in some other state, not just zero. So of course we can do that. We could start in a different state, but the thing is that we could simply make another little circuit here to prepare that state that we were trying to prepare, and then instead start this preparation circuit from the zero state. Because if we can, making a quantum algorithm, basically what that is about is you're preparing any state, right? We proved that, we didn't prove, I just stated that by combining all these different gates, we can make an arbitrary quantum circuit, which presumably means that we can make any quantum state too, right? So we should be able to make a quantum circuit to prepare that state. And then if we just call that whole thing our bigger quantum algorithm, so quantum U L dash, then of course it's still we can view it like that. So so it's in this sense that we can start in the zero state and there's sort of no loss of generality, because we can simply push the preparation into the quantum circuit itself. Okay. One bit of sort of caution here. When you write quantum circuits, as I said, basically the sequence goes left to right, right? But actually, if you write down a sequence of gates, actually the convention is, well, it's not really convention, but I mean the notation is the reverse, right? So for example, in this example that I just did, where we did the preparation and then the algorithm, if I were to write that in sort of operator notation, then I would write it actually UL, and then that acting on U prep, and that acting on this initial state, right? So just always be careful that when you're drawing a quantum circuit, actually everything is kind of the opposite order. Yeah, it's just one thing to look out for. Okay, now I also said that the measurement basis is always in the 0-1 basis. Again, this seems like a unnecessary restriction because, previous lectures I went to all the trouble of saying, well, these measurement boxes, it's got this dial, you can measure in all these different bases, and so, that's what's special about quantum mechanics and blah, 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 and after all that, I just say, we're just going to measure in the 0-1 basis. So the reason why is it's a little bit similar to the preparation argument, which is that actually we can always put a little basis rotation circuit before the measurement. And that actually, and if we consider this thing in the red box to be our more generalized measurement in some other basis, then all this stuff stuff here in the red box can be considered the measurement, the more generalized measurement. So, so again, just like with the preparation example, if I now combine that basis rotation part of it with the algorithm itself, and then just call that U algorithm dash, then again, measurement itself can be done in 0-1 basis without any loss of generality. Okay. Yeah, and here is sort of the proof, if you like, of why I can just combine that basis rotation with the 0-1 measurement basis. And the way that we can do that is, so consider this Mn to be our measurement operator that's done in the 0-1 basis, right? So n is just our 0-1 basis state. And then now let's look at this combined thing, which is this rotation, or unitary rotation, U basis. This is the thing that changes the basis, right? And let's think of the thing in the red box that this red box here, as M, the measurement operator, but more general basis, okay? And this general unitary is always some matrix which can be written in this form, because these M's, this is in some, these are basically a set of different orthogonal states. And so, something wrong here. Oh, okay. Okay, I think all I did here was to, yeah. Okay, so essentially what I did here is, so this is a general unitary rotation here. And if we just redefine this as our basis, so this is the basis that we're actually going to be measuring in, then we can equally write this as n times this new basis. And then what we're going to do is just multiply this one by this unitary matrix. So we said Mn is n, and this unitary here, which is the circuit that does the rotation. So this is, okay, so I'm writing it as Mn. So this is some general matrix, right? And these M's are just in also the 0-1 basis, but then there could be some, complicated coefficients here. Right? But what I'm doing here is just to, let's define this thing called Bn, which okay, might be a bit easier if I define the conjugate vector actually. Define Bn conjugate vector as being, this one is m dash u m dash. Okay, I'm just defining that thing, right? And then I can just put that thing in there. Sorry, this should be n. Then I can put that in there. And then I can basically consider all this u stuff to be in some more general basis. And then now so my definition of the more general measurement is mn times u. And then, so this thing is n. And let's use this form that I wrote down here, m bm. And these are some orthogonal, well, these are just the usual 0, 1 basis states, right? So we need n is actually equal to m here in order for this to be non-zero. So actually this sum actually collapses, and what we end up having is n b n. This thing is 1, and then we have that. And basically what this is doing is that it is changing the basis of this projector here, so that when we apply this more mn gen to some state, what's going to happen is that this is going to be n times whatever this basis thing here is, this coefficient. And if we want to work out the probability of this, then it's this mn gen that. So it's basically this thing multiplied by the conjugate vector. So it's going to be bm psi squared n 1. So the probability is the psi, the state, times by this basis squared. That's sort of the general kind of proof. If you like, we could do a simpler example, but you might like to not worry about it too much. Basically, the main result is that if you combine this basis rotation with just before the measurements, then it's equivalent to writing it in, or doing a measurement in any particular basis. So that's the main result. That's the proof. If you like, we can do a simpler example, maybe next lecture. But yeah. Any questions? Okay, all right. Well, we'll leave it there, and yeah, if you want to discuss this more, then